In this video, we will discuss these topics. We will see that polar protic solvents contain OH or NH bonds, and that polar aprotic solvents do not. We will learn that SN2 reactions occur more quickly in polar aprotic solvents, and we will learn the reason for that SN2 pattern. We will also learn that SN1 reactions occur more quickly in polar protic solvents, but we will not discuss the reason for the SN1 pattern in this video, and that's because the reason for the SN1 pattern is more subtle and is also less frequently tested than for the SN2 pattern. So for simplicity, I'm going to leave that out of the video. If you're interested, you should be able to find the reason for the SN1 pattern in your textbook. If you find that this video moves too slowly, keep in mind that you can use the problems document and the answers document to supplement or replace the video. If this material is intuitive for you, then you might find that this brief summary right here is just about all you need to get the problems in the problems document correct. Also keep in mind that this video builds on the ideas that we covered in the previous video series on SN2 and SN1 reactions. Let me begin by asking you, how would you define the term polar molecule? I'm going to be asking you a lot of questions in this video, and I hope that each time I ask a question, I hope that you'll pause the video and come up with your own answer. Here's an answer. A polar molecule contains delta charges. By the way, this is not really a complete definition of what a polar molecule is, but this is a good enough definition for most purposes in organic chemistry. Now, our goal in this video is to discuss solvents. So let's apply that idea of a polar molecule to determine which of these are polar solvents. Which of these are polar solvents? Well, do you see these are all polar solvents because they all contain delta charges. For example, oxygen is more electronegative than hydrogen. So as a result, the oxygen would end up with a delta negative charge and the hydrogen with a delta positive charge. Oxygen wants electrons more than hydrogen, so the oxygen would pull the electrons in the bond closer to itself, giving itself a partial negative charge. For the same reason, this oxygen is delta negative and this hydrogen is delta positive. Oxygen is again more electronegative than carbon, so this oxygen is delta negative, this carbon is delta positive. Oxygen is more electronegative than sulfur. So here's a delta negative and a delta positive, and we could assign delta negatives and delta positives here too. I'm not assigning all the delta negatives and delta positives in these molecules. There's more delta negatives and delta positives, but this should be enough to convince you that all of these solvents are polar. These are all polar solvents. In previous video series, we've seen that these are solvents that are commonly used for SN2, SN1, E2, and E1 reactions. And now we can see these are all polar solvents. By the way, I've used the idea here that the electronegativity of hydrogen is similar to the electronegativity of carbon. That's how I know that oxygen is more electronegative than hydrogen. I know that oxygen is more electronegative than carbon because oxygen is to the right of carbon in the periodic table. And I know that oxygen is more electronegative than hydrogen because hydrogen is similar to carbon in electronegativity. I discussed how to determine delta negatives and delta positives in much more detail in the SN2 video series. Now, for our next concept, do you know how to identify whether a solvent is protic or aprotic? Could you identify which of these is protic or aprotic? How do you identify which solvents are protic and which are aprotic? Well, we haven't covered that yet, but here's the answer. For our purposes, we can define a protic solvent as a solvent that contains one or more OH or NH covalent bonds. An aprotic solvent is a solvent that does not contain any OH or NH covalent bonds. So take a moment to memorize these definitions. Now next, let's try to identify which of these common solvents is protic and which of these common solvents is aprotic. Pause the video and try to identify which of these solvents is protic and which is aprotic. I hope you gave that a shot. Well, let's go through that. Starting with water, well, water does contain an OH covalent bond. In fact, it contains two OH covalent bonds. So water meets the criterion for being a protic solvent. And alcohols also contain one OH covalent bond. Any alcohol contains one OH covalent bond, as you can see from these pictures. So alcohols are also protic solvents. Now, how about DMSO? There are no OH or NH covalent bonds in DMSO. So DMSO is an aprotic solvent. Now, notice there are hydrogens in this molecule, right? There were 3 hidden hydrogens on this carbon, and there's another 3 hidden hydrogens on this carbon, but those hydrogens are forming carbon-hydrogen covalent bonds. So notice that a carbon-hydrogen covalent bond is not good enough to call a solvent protic. To be protic, it has to have an OH or an NH bond, not a CH bond. So notice that aprotic solvents certainly do contain hydrogens. Aprotic solvents certainly do contain hydrogens, but they don't contain any OH-NH bonds. Acetone has no OH or NH bonds, so acetone is aprotic. Acetone has 6 hidden hydrogens, but none of them is connected to an oxygen or a nitrogen. And DMF is again aprotic because there are no OH or NH bonds. There is an oxygen, but it's not connected to any hydrogens. There's a nitrogen, but it's not connected to any hydrogens. And there are plenty of hydrogens, but none of the hydrogens are connected to an oxygen or a nitrogen. Remember that Me here stands for a methyl group. Well, the methyl groups contain CH bonds, but they don't contain any OH or NH bonds. So we can see that all the solvents in this column were protic, and all the solvents in this column were aprotic. So I'll label that this left-hand column contains polar protic solvents, and the right-hand column contains polar aprotic solvents. Remember, we've already discussed that all of these solvents are polar because all of these solvents contain delta charges. All of these solvents are polar. Some of the solvents are polar protic, and some of the solvents are polar aprotic. Next, we have to learn how polar protic and polar aprotic solvents affect the rate for SN1 and SN2. Have you learned that? Do you know how do polar protic and polar aprotic solvents affect the rates for SN1 and SN2 reactions? Well, here's the answer. An SN2 reaction is faster in a polar aprotic solvent and slower in a polar protic solvent. An SN1 reaction is faster in a polar protic solvent and slower in a polar aprotic solvent. Now would be a good time to pause the video and memorize those facts. Now, how can you tell whether a solvent is protic or aprotic? Well, if the structure of the solvent is drawn for you, then it should be easy to use this rule to determine if the solvent is protic or aprotic. But sometimes the structure of the solvent isn't shown. Sometimes the solvent is just named. In particular, the problem might just say that the solvent is DMSO or acetone or DMF, and then you won't be given the structure. So for those cases, you should have memorized. You should have memorized that DMSO and DMF and acetone are polar aprotic solvents. Now would be a good time to pause the video and memorize that DMSO, acetone, and DMF are polar aprotic solvents. Please pause the video and try this problem. I hope you actually did try the problem. Now let's discuss it together. We can start by numbering. I'm going to give both of these molecules the same numbers because they're the same molecule and because our whole goal is to compare these two molecules. I won't bother numbering this carbon because it won't play an important role in the reaction. And do you know what ET stands for? ET stands for an ethyl group. There's no convenient way to number these carbons in this notation, so I won't number those. Look for ionic bonds. You should always look for an ionic bond when you're starting a problem. When you see a metal-non-metal bond, that's an ionic bond, and you should draw in the formal charges. So we should know that the metal here has a positive formal charge, and the non-metal is negative. Because non-metals want electrons, and metals want to give up electrons. So the electrons will move to the non-metal to give it the negative formal charge. So assigning roles, we can say that something with a negative formal charge is likely to act as a nucleophile or as a base. Nucleophiles and bases are electron donors, so a negative charge would make something want to act like a nucleophile or a base. You should know that positive sodium is a spectator that won't participate in the reaction, and you should recognize this as a sulfonate leaving group. These molecules are called alkyl sulfonates. Here's the general structure of an alkyl sulfonate. The sulfonate group is a good leaving group. In an alkyl sulfonate, the alpha carbon is the carbon attached to the oxygen. So carbon 3 is the alpha carbon here, and carbon 3 is the alpha carbon here. This is not the alpha carbon because it's attached to the sulfur, not to the oxygen. Now we can assign roles. I meant to say now we can choose our mechanism. We'll use our table to choose the mechanism. We can use this table to choose the mechanism for an alkyl sulfonate. We need to notice that this alpha carbon is primary. In both cases, we have a primary alpha carbon because carbon 3 is attached to one carbon chain, starting with carbon 2. A primary alpha carbon puts us in the top row of the table. Br minus puts us in the middle column of the table. So the table predicts an SN2 mechanism for both reaction A and reaction B. What role are the DMF and the ETOH playing? The DMF and the ETOH are the solvents. Notice that for this reaction, we're going to prefer to use the Br minus as the nucleophile rather than the ETOH. The negative charge is going to make this Br minus more reactive than the ETOH. You can see from this chart that alcohols can be used as nucleophiles and bases, but only if there's no better nucleophile or base present. So we could use ETOH as a nucleophile or base, but only if there's nothing better present. Well, Br minus, because of its negative charge, will be better and more reactive. So we're going to use the Br minus in the reaction rather than the solvent. And notice that DMF is one of these solvents which we simply don't use as participants in SN2, SN1, E2, or E1 reactions. So notice that we don't actually use the solvent to determine what the mechanism will be. We didn't use these solvents, DMF and ETOH, to determine what the mechanism would be. Instead, we just focused on the type of alpha carbon and the type of nucleophile or base that we were going to use. So we use this table. Generally speaking, using this table is the best approach for figuring out the mechanism, and the table doesn't rely on what the solvent is. So we can say now that since this is going to be an SN2 reaction, SN2 reactions use a nucleophile rather than a base. So I can say now that the Br minus will act as a nucleophile in the reaction. We know that the neutral oxygen in the sulfonate will be the leaving group because it's attached to the alpha carbon. Carbon 3, the alpha carbon here, has a delta positive charge because it's attached to this electronegative oxygen, and that delta positive charge makes carbon 3 electrophilic. So we expect carbon 3 to act as the electrophile. Now, all the steps that I just discussed are discussed in much more detail in the video series on SN2 reactions. So if you had any trouble following any of those steps that we went through to determine that these were both SN2 mechanisms, You can find more information about all of those steps and more information about how to use this table in the SN2 reactions video series. Now, it's not actually necessary here to draw the mechanisms. It's not actually necessary here to draw the mechanisms to answer the question that's being asked. So how do we answer this question? Well, to compare these reactions, we have to look for a difference between the two reactions. How are these reactions different? It's useless to compare the alpha carbons because they have the same alpha carbon. It's no good comparing the leaving groups or the nucleophiles because they both have the same leaving group and nucleophile. So now is the time that we should pay attention to the solvents. The one difference between reaction A and reaction B is the solvents. So we have to decide which of these solvents will be better for an SN2 reaction. Well, we can see that the ETOH alcohol is a protic solvent because it has an OH bond. So we know that reaction B is using a polar protic solvent because of the OH bond. Now the DMF here, they didn't show us the structure of DMF. So you need to have memorized that DMF has a structure which makes it a polar aprotic solvent. Here is the structure of DMF. Notice that DMF has no OH or NH bonds, so it is indeed a polar aprotic solvent. And you should have memorized, we've learned in this video, that a polar aprotic solvent is better for SN2, and a polar protic solvent is worse for SN2. So that gives us our answer. Reaction A will occur at the faster rate because we've learned that an SN2 reaction is sped up by a polar aprotic solvent and slowed down by a polar protic solvent. So here are some of the ideas that we learned earlier that we applied to this problem. We knew that the ETOH was a protic solvent because it contains an OH bond. I hope you recognize that this is ethyl alcohol. Remember, the ET stands for an ethyl group, so this is ethyl alcohol. It's a protic solvent, and we have memorized that DMF is one of the aprotic solvents. We know that although they didn't show us the structure for DMF does not contain any OH or NH bonds. And we've also memorized that an SN2 reaction is faster in a polar aprotic solvent. Faster for reaction A, and an SN2 reaction is slower in a polar protic solvent. Slower for reaction B. Notice that it was crucial here to first determine the mechanism. First, we had to determine that the mechanism was SN2. If we hadn't known what the mechanism is, we wouldn't know the answer, because remember that the answer would reverse for an SN1 mechanism. For an SN1 mechanism, the answer would reverse. So the first step for carrying out this type of problem is to determine the mechanism. Notice the problem doesn't say you have to determine the mechanism, but it should just be a natural step in most OChem problems that you start by determining what mechanism will occur. And then we use the mechanism here to determine the answer. Remember that we used that table to determine the mechanism. And I discussed how to use that table in more detail in the series on SN2 mechanisms. Pause the video and try this problem. Now let's discuss. Start by numbering. I won't number these carbons because these are in a solvent that won't participate in the reaction. We should look for ionic bonds. There are no ionic bonds, so there's no formal charges we need to assign, so we can start trying to assign roles. Well, normally we'd look for a negative formal charge as a nucleophile or base. Since there are no negative formal charges, the next best thing here is the neutral oxygen. The neutral oxygen can act as a nucleophile or a base because it has a lone pair. An atom with a lone pair also has some willingness to donate electrons, and that's what nucleophiles and bases do. Similarly here, we expect the water to act as the nucleophile or the base. This molecule we should recognize as an acetone solvent. Acetone solvent, and we should know that acetone solvent is a solvent that's not used as a participant for SN2, SN1, E2, or E1 reactions. So we don't expect this acetone solvent to participate in the reaction, so we'll use the oxygen in the water instead. Neutral chlorine is a good leaving group, which makes carbon 1 into our alpha carbon. And that in both cases is a secondary alpha carbon. Carbon 1 is attached to two carbon chains, a carbon chain that starts with carbon 6 and another carbon chain that starts with carbon 2. We use the table to determine the mechanism. A secondary alpha carbon puts us in the middle row of the table, and in both cases we're using the neutral oxygen in water as our nucleophile, and that puts us in the left-hand column of the table. So we expect the major reaction here to be SN1. We should write down that we're going to be focusing on the SN1 mechanism in both of these cases. If you had any difficulty following any of those steps for how I determined that these mechanisms would be SN1, you should watch or rewatch my earlier video series on SN1 reactions. Since the reaction will be SN1, we can update and say that the water will be acting as a nucleophile. SN1 reactions use the water as a nucleophile in the main reaction. Now, to choose which of these reactions is faster, we have to look for some difference between them. They have the same mechanism, the same leaving group, the same alpha carbon, the same nucleophile. So what's the difference? Well, the difference is the solvents. Now, what was the solvent in reaction A? The solvent in reaction A is the water. Notice that water can be both a nucleophile and a solvent. It's no contradiction to say that you're using the solvent as a nucleophile. In fact, remember from this table that the table specifies that water and alcohols can be used as nucleophiles for SN1, but only if there's no better nucleophile present. Well, that was exactly the case here. There was no better nucleophile present for reaction A, so we used the water as the nucleophile. In fact, the same thing is true in reaction B. There's no better nucleophile present than the water for reaction B, so again, reaction B uses the water as the SN1 nucleophile. So in reaction A, the water is the solvent, and we know that that is a polar protic solvent. It's protic because it has an OH bond. In fact, it has two OH bonds. Now, what's the solvent in reaction B? Well, notice that in reaction B, we have 50% water and 50%, a mixture, 50% water and 50% acetone. That means that the solvent is a mixture of water and acetone. The solvent here is a mixture of both water and acetone, a solvent made of 50% water and 50% acetone. This molecule is acetone. Well, we know that the water is a polar protic solvent. But we know that the acetone is a polar aprotic solvent because the acetone has no OH or NH bonds, so it's an aprotic solvent. Well, we know that polar protic solvents are better for SN1. Therefore, reaction A will be faster. Because reaction A uses a 100% polar protic solvent, which is best for SN1. Now, reaction B also has 50% of that polar protic solvent, which is good for SN1, but it also has 50% of this polar aprotic solvent, which is less good for SN1. So because of this 50% presence of the less good polar aprotic solvent, the SN1 mechanism will be slower for reaction B than for reaction A. So we used these ideas again. We recognized that water was polar protic because of its OH bond. We recognized that the acetone is aprotic because it has no OH or NH bonds. And we recognized that the 50% acetone in reaction B would slow down the SN1 reaction. SN1 is slower in a polar aprotic solvent. Having 100% water would be better because water is polar protic, and a polar protic solvent is better for SN1. Again, notice that it was crucial to know what the mechanism was. our results would reverse if we were doing an SN2 mechanism. So you have to start by determining the mechanism. Remember that we used the table to determine the mechanism. We used this table to determine the mechanism. That means that you have to have this table memorized. Unless you're allowed to use notes during your exams, you'll need to have this table memorized in order to be able to use it to determine the mechanism. If you haven't done so already, now would be a good time to sit down and memorize this table, because this is the best way usually to figure out the mechanism. By the way, you might sometimes see this mixture of 50% water and 50% acetone described in words as 50% aqueous acetone. Do you see why 50% aqueous acetone is the same as this mixture? The aqueous, the word aqueous refers to water. Aqueous refers to water, and of course acetone refers to acetone. So 50% aqueous acetone means 50% aqueous, 50% water, and 50% acetone. So this combination of solvents could be described this way or this way. So we've seen that an SN2 reaction occurs faster in a polar aprotic solvent and more slowly in a polar protic solvent. So the next thing that we need to do in this video is explain why this is true. We need to explain why a polar aprotic solvent speeds up an SN2 and why a polar protic solvent slows down an SN2. Why is it useful for you to learn that? For one thing, this is oftentimes tested on exams. For example, for this type of problem, it would be common for the professor to require you to explain why reaction A is faster than for reaction B. And for full credit, you would have to explain why SN2 occurs more quickly in a polar aprotic versus a polar protic solvent. So we need to learn why SN2 is faster in polar aprotic solvents, because that could be tested on exams. And also just because it'll help to give you a deeper insight. Knowing the explanation will help to give you a deeper insight into SN2 and into these solvents, and maybe help you to remember this pattern better. On the other hand, I am not going to explain this pattern in this video. An SN1 reaction is faster in a polar protic solvent, but I'm not going to give the explanation for why that is in this video. The reason I'm not going to go over that explanation is, for one thing, this explanation, I think, is tested less frequently than this one. This explanation is tested less frequently, so there's less value to going over this. And also, this explanation is more subtle, is a more subtle or more complicated explanation than this one. So for simplicity, and because it's tested less frequently, I'm not going to cover this explanation in this video. If you're interested, or if you think that your professor might test this, you should be able to find an explanation in your textbook. So now let's proceed to explain why an SN2 reaction is faster in a polar aprotic solvent. Well, in the SN2 reactions video series, here's some important information. Here's some important information that I covered in the SN2 video series about factors that affect the rate of an SN2 reaction. The key factor I want to focus on is the big obstacle to an SN2 reaction. We could say that the big obstacle to an SN2 reaction is steric hindrance. Steric hindrance that blocks the nucleophile from joining the alpha carbon. The big obstacle to an SN2 reaction is steric hindrance that blocks the nucleophile from joining the alpha carbon. That's why SN2 is fastest for a methyl alpha carbon and slowest for a tertiary alpha carbon. SN2 is fastest for a methyl alpha carbon because methyl alpha carbons have the least steric hindrance that can block the nucleophile from joining the alpha carbon. SN2 reactions are slowest for tertiary alpha carbons because those have the most steric hindrance that can block the nucleophile from joining the alpha carbon. Why is this steric hindrance that blocks the nucleophile an important factor for SN2? Well, in that earlier video series, we explained that it comes down to thinking about the rate-determining step. The rate-determining step is the slowest difficult step in a reaction. Anything that affects the rate-determining step will affect the rate of the reaction. Well, an SN2 mechanism has only one step. Therefore, that single step is the rate determining step for an SN2. So this single step is the rate determining step for an SN2. And notice that during this rate determining step, the nucleophile has to join the alpha carbon. Since the nucleophile has to join the alpha carbon during the rate determining step for SN2, anything that can block the nucleophile from joining the alpha carbon will slow down the rate of the SN2 mechanism. By the way, do you know what steric hindrance means? Steric hindrance is a fancy term for things getting in each other's way. So anything that gets in the way of the nucleophile and blocks it from joining the alpha carbon would be a big obstacle to SN2 because the nucleophile has to join the alpha carbon during the rate determining step for SN2. And anything that affects the rate determining step will affect the rate of a reaction. Now let's think about what happens when you dissolve a nucleophile in a solvent. Remember that the solvent is a liquid that you dissolve the nucleophile in. That means that when you put the nucleophilic substance into the liquid solvent, the nucleophile molecules are separated and split up from each other. They're separated from each other and they become surrounded and separated from each other by the solvent molecules. But how tightly will the nucleophilic molecules or atoms or ions be surrounded by the solvent molecules? A polar protic solvent will solvate the nucleophile tightly. A polar protic solvent will create a tight solvation shell, a shell of solvent molecules around the nucleophile. On the other hand, a polar aprotic solvent solvates the nucleophile more loosely. I've tried to show that in these two pictures. Here's a picture of the nucleophile being tightly solvated by a shell of solvent molecules, a shell of polar protic solvent molecules. And here's a picture of the nucleophile being solvated more loosely by polar aprotic solvent molecules. Well, now you should be able to take this information and decide which of these solvents is better for SN2 and why. Pause the video and decide which solvent is better for SN2, a polar protic or a polar aprotic solvent, and explain why it's better. Well, here's the answer. Remember that we've seen that the big obstacle to an SN2 reaction is steric hindrance that can block the nucleophile from joining the alpha carbon. Well, it should be plain that this tight solvation shell creates a lot of steric hindrance that can block the nucleophile from attacking the alpha carbon. Well, it should be plain that this tight solvation shell creates more steric hindrance around the nucleophile that can block the nucleophile from attacking the alpha carbon. It would be difficult for this nucleophile to attack this alpha carbon. It's going to be tough for this nucleophile to get close enough to attack this alpha carbon because it's surrounded so closely on all sides by these pesky solvent molecules. So that the solvent molecules, this solvation shell, is creating steric hindrance that can block the nucleophile from joining the alpha carbon. On the other hand, in this case where the nucleophile is solvated more loosely by the solvent molecules, it will be much easier for the nucleophile to get close enough to the alpha carbon to attack it for an SN2 reaction. So the polar aprotic solvent is better for SN2 because it creates less steric hindrance around the nucleophile because the polar aprotic solvent molecules are solvating the nucleophile more loosely. The polar protic solvent is worse for SN2 because it creates more steric hindrance that blocks the nucleophile from attacking the alpha carbon because the polar protic solvent creates a tight shell of solvent molecules around the nucleophile. Now, why does the polar protic solvent solvate the nucleophile more tightly? Why does the polar aprotic solvent solvate the nucleophile more loosely? Well, I will give an explanation for that at the end of this video. I'm not going to go into that explanation right now because the fact is that for most professors, this is as much explanation as you will need to give to get exam problems right. For most professors, for most problems, most professors would accept these ideas as a sufficient explanation for most exam problems. So we'll try some more problems like you might see on an exam now. And for those who are interested, at the end of the video, I'll put the extra explanation for why the polar protic solvent solvates nucleophiles more tightly. Please pause the video and try this problem. Now let's discuss. We can start by numbering. This parenthesis represents two separate methyl groups. That makes these carbons difficult to number, so I won't bother numbering those. And there's no need to number this carbon or this carbon or this carbon because those are in the solvents, which won't participate in the reaction. I guess it is useful, though, to number the products that we were given. Make sure that you number your products consistently with your starting materials. We don't need to look for ionic bonds here. The formal charge was already given for us on the N3, so we can start assigning roles. When we see a negative charge, we expect that atom to act like a nucleophile or like a base, because nucleophiles and bases are electron donors. And a negative charge makes you want to donate electrons. A neutral bromine looks like a good leaving group, which means that carbon 2 is going to be our alpha carbon. And we notice that that's a primary alpha carbon. So we're ready now to choose a mechanism. Now the next step is to determine the mechanism. To determine the mechanism, first look at the products that we're given. From these products, we can tell that the mechanism for both reactions is a substitution reaction, because in both cases it appears that the N3 has substituted into the position that was formerly occupied by the bromine. So from these products, we can see these are both substitution reactions, but that doesn't tell us whether the mechanism should be SN1 or SN2. So now we have to use our table to determine whether the mechanism is SN1 or SN2. By the way, notice I think that it helps to, you can see here that numbering the products and the starting materials consistently helps us to see that this is a substitution reaction. Numbering forces you to recognize that these carbons are the same as these carbons, which I think helps you to see that the difference here has been a substitution between the products and the starting materials. Our table. With a primary alpha carbon, we're in the top row of the table. Now N3- can be found here in the middle column of the table. So notice that N3- is a specific nucleophile that you find in the middle of the table. It's not the same as an ordinary negative nitrogen. N3- is different from an ordinary negative nitrogen. Those are in two separate columns. So our table predicts that we're going to have an SN2 mechanism, and it's important to make a note of that. Both reaction A and reaction B are predicted to be SN2 mechanisms. Notice that we don't use the solvents to determine the mechanism, we use the table to determine the mechanism. Now, we know that SN2 uses a nucleophile, not a base, so we can update here. Carbon 2 is attached to bromine, which is more electronegative, which means that carbon 2 will have a delta positive charge. And that's the clue that carbon 2 can act as our electrophile for our SN2 reactions. It's good to label the roles that atoms will play in the reactions. Now, to decide which reaction is faster, we have to look for some difference between the reactions. Well, the electrophiles, leaving groups, and nucleophiles are the same, so we have to compare the solvents. Well, notice that there's an OH bond in this solvent. There's an OH bond in this solvent, and that means that this is a polar protic solvent. There are no OH or NH bonds in this solvent. There are 6 CH bonds, but there are no OH or NH bonds. That makes this a polar aprotic solvent. A polar aprotic solvent. You should recognize that this solvent is methanol, methyl alcohol, and you should recognize that this solvent is DMSO. This is the structure of the DMSO solvent. So we're using the methanol solvent and the DMSO solvent that we've already seen in our chart. Now we know that both reactions are SN2 reactions, and we know that SN2 is faster in a polar aprotic solvent and slower in a polar protic solvent. So here's our answer. Reaction A will occur faster. because an SN2 mechanism occurs more quickly in a polar aprotic solvent. Now remember, this problem required us to justify our answer, so we won't get credit or full credit without an explanation. Well, the explanation is that the nucleophile is solvated more loosely in the polar aprotic solvent, which makes it easier for the nucleophile to attack the alpha carbon in the polar aprotic solvent. The nucleophile is solvated tightly by a tight solvation shell in the polar protic solvent in reaction B, which creates steric hindrance that makes it difficult for the nucleophile to attack the alpha carbon in the polar protic solvent. So SN2 is faster in a polar aprotic solvent. This paragraph here is probably more detailed than you would need for full credit on an exam. I gave a little extra detail for clarity. It would probably be good enough to say that reaction A is faster because it uses a polar aprotic solvent, and that the nucleophile is solvated more loosely in a polar aprotic solvent than in a polar protic solvent. Notice that a crucial part of our solution was determining the mechanism, because the answer would be reversed if we were using an SN1 mechanism. So make sure you use the table to determine the mechanism. Please pause the video and try this problem. Now we can discuss. We can start by numbering, including this carbon, and make sure that you also number the products consistently with the starting materials. On the other hand, it's not necessary to number these carbons because these solvents don't participate in the reaction. Now we look for an ionic bond, and we find an ionic bond between the sodium and the carbon. So we should draw in the ionic bonds there. The sodium metal will be positive, and the carbon will be negative because it's ionically bonded to the sodium. We expect neutral bromine to be our leaving group. That makes carbon 3 the alpha carbon. Carbon 3 is a secondary alpha carbon. So now we want to choose the mechanism. Now when you're choosing the mechanism, first you should look at the products here to get a hint as to the mechanism. From looking at the products, we can see that this is a substitution reaction, where we are substituting the cyanide into the place of the bromine. So the products tell us that the mechanism will be a substitution reaction, but that doesn't tell us whether it's SN1 or SN2, two different types of substitution. Let's use our table. A secondary alpha carbon puts us in the middle row of the table, and this CN- nucleophile is a specific nucleophile that you can find in the middle column of the table. CN-, that's actually called the cyanide nucleophile. So that tells us that we're going to be using an SN2 mechanism for both reaction A and reaction B. Notice that we didn't use the solvents to determine the mechanism. We used the table. So I've been assuming here that the CN- is going to be the nucleophile. I should have specified that specifically. A nucleophile or a base is an electron donor, so a negative charge makes something nucleophilic or basic. Now that we know that the mechanism is SN2, we know that the cyanide will act like a nucleophile, not like a base. Carbon 3 has a delta positive charge because it's attached to the bromine, which gives us a reason to think that carbon 3 will act as our electrophile. And now we can see that these two reactions have the same alpha carbon, the same leaving group, and the same nucleophile. So how do we find a difference between them? The difference is the solvents. We can see that this solvent for reaction A has an OH bond, so it's a polar protic solvent. And this solvent for reaction B has no OH or NH bonds. It has 6 CH bonds, but no OH or NH bonds. So this is a polar aprotic solvent. You should recognize this solvent as methanol, methyl alcohol, and you should recognize this solvent as acetone. So in this problem, we're using these two solvents from our chart, acetone and methyl alcohol. And we need to use the idea that an SN2 reaction is faster in a polar aprotic solvent and slower in a polar protic solvent. Here's our answer. Reaction B will be faster. Reaction B will be faster. For credit, you need to justify your answer. Reaction B is faster because it uses a polar aprotic solvent, which solvates the nucleophile more loosely and makes it easier for the nucleophile to attack. Reaction A is slower because it uses a polar protic solvent, which forms a tight solvation shell and creates steric hindrance that prevents the nucleophile from attacking the alpha carbon. This is probably more detailed than you would need for full credit. It might be enough just to say that reaction B is faster because it uses a polar aprotic solvent, which solvates the nucleophile more loosely, and the polar protic solvent in reaction A solvates the nucleophile more tightly. Remember that it was crucial for this problem to determine the correct mechanism. If the mechanism were SN1, the answer would be reversed. Please pause the video and try this problem. Now we can discuss. We can start by numbering. There are no ionic bonds to discover. We have to decide what 50% aqueous acetone means. I actually explained that in a previous problem. Do you know what aqueous means? Aqueous means water. So this means 50% aqueous, that's 50% water, and 50% acetone. So that means there are two solvents for this reaction, two solvents. The solvent is made up of 50% water and 50% acetone. That's what 50% aqueous acetone means. Well, water is a solvent that you can use as a nucleophile if there's nothing better around. There's nothing better here to use than the water as our nucleophile, so we expect to use the water as the nucleophile, or possibly as a base. Because of the lone pair on the oxygen, water can act like a nucleophile or like a base. We should have memorized that acetone is a solvent that doesn't participate in these types of reactions that we're working with right now. The neutral chlorine looks like our leaving group. Makes carbon 1 the alpha carbon. Carbon 1 is a tertiary alpha carbon attached to 3 carbon chains, carbon 8, carbon 2, and carbon 5. We use the table to determine our mechanism. A tertiary alpha carbon puts us in the bottom row of the table, and the neutral oxygen in water puts us in the left-hand column of the table. So the table predicts that the major mechanism will be SN1. Without any other clues, we'll go with the major mechanism, SN1. That tells us that the water really will act like a nucleophile, not like a base. Now, to determine which SN1 is faster, we look for the difference between the reactions. The reactions of the same leaving group and alpha carbon, the difference is the solvents. This solvent is pure water, which we know is a polar protic solvent because it has 2 OH bonds. Reaction B uses 2 different solvents. One solvent is water again, but the other solvent is acetone, which we know is a polar aprotic solvent. Notice that the structure of acetone wasn't drawn for you here, so you're just expected to have memorized in this problem. In this problem, you're just expected to have memorized that acetone is a polar aprotic solvent. So reaction A uses a purely polar protic solvent, whereas reaction B uses 50% polar protic solvent and 50% polar aprotic solvent. So we're using these 2 solvents from our chart, water and acetone. And remember that this problem expects you to have memorized that acetone is a polar aprotic solvent. You can see that it really is polar aprotic because there's no OH or NH bonds in the structure of acetone. And remember, the chart reminds us that acetone doesn't participate in SN1 and SN2 reactions. That's why we're expecting to use the water as the nucleophile. And that's why we're expecting to use the water as the participant in the reaction rather than the acetone. So our answer to the question is that reaction A is faster because SN1 mechanisms are faster in a polar protic solvent. Reaction B uses 50% polar protic solvent, but also 50% polar aprotic solvent that will help to slow down the reaction. Now, we haven't really explained or justified our answer because we haven't said why SN1 mechanisms are faster in a polar protic solvent. And as I've mentioned before, I'm actually not going to cover that explanation in this video because it's more subtle than the explanation for SN2 mechanisms, and it's also not really tested that frequently. You can find that explanation in your textbook if you're concerned about that. I can give you a little bit of an explanation for this trend, though. Remember that polar protic solvents are worse for SN2 because they create more steric hindrance around the nucleophile. And the big obstacle to SN2 is steric hindrance. Well, as I discussed in the SN1 video series, steric hindrance is not a big obstacle to SN1. Steric hindrance is not a big obstacle to SN1. And you can see why from the rate determining step. So remember that an SN1 mechanism is a two-step mechanism. And the rate determining step is the first step where the leaving group leaves the alpha carbon, forming the carbocation. This first step is the rate determining step. This is the difficult step because it's difficult to form the positive charge on the carbocation, and it's difficult to form an incomplete octet on the carbocation. So the first step is the difficult step. Well, notice that the nucleophile doesn't participate in the rate determining step for SN1. The nucleophile participates in the easy second step for SN1. The nucleophile doesn't participate in the difficult, slow first rate determining step for SN1. And as a result, steric hindrance that blocks the nucleophile is not a big obstacle to SN1. Remember, anything that does not affect the rate determining step will not affect the rate of the reaction. Since the nucleophile does not attack the alpha carbon during the rate determining step for SN1, steric hindrance that blocks the nucleophile is not a big obstacle for SN1. So now we can see why this logic that worked for SN2 isn't going to work for SN1. Polar protic solvents are worse for SN2 because of the steric hindrance they create around the nucleophile. Well, we wouldn't expect that to matter much for SN1 because steric hindrance doesn't matter that much for SN1 because the nucleophile doesn't join the alpha carbon in the rate determining step. So we can see why the logic that applied to SN2 mechanisms doesn't apply to SN1. We know that polar protic solvents are worse for SN2 because of the steric hindrance they create around the nucleophile. There's no reason to expect a polar protic solvent to be worse for SN1 because the steric hindrance around the nucleophile is not a big obstacle for SN1. Now, that's not a full explanation of the solvent effects for SN1. So now we've explained why polar protic solvents are not worse for SN1, but we still haven't explained why polar protic solvents are better for SN1. And again, actually, I'm not going to explain in this video why polar protic solvents are better for SN1. That involves some more subtle issues that are less frequently tested. So I'll let you look those up in the textbook if you're interested. Please pause the video and try this problem. Now let's discuss. Well, in this case, we don't use the table to determine the mechanism. The mechanism is described for us. We know that this will be an SN2 mechanism because the problem told us so. We know that the key way to judge the solvent is whether it's protic or aprotic. Well, notice that this solvent has two nitrogen-hydrogen bonds. So those nitrogen-hydrogen bonds make this a polar protic solvent. This solvent is not a solvent that was specifically mentioned in our chart of solvents earlier. But even though we haven't seen this solvent before, we can recognize that it is a protic solvent because it has an NH bond. Remember, a protic solvent is a solvent that contains one or more OH or NH bonds. On the other hand, this solvent contains no OH or NH bonds, so this is a polar aprotic solvent. And this contains two OH bonds, so this is a polar protic solvent. Notice that this is another solvent that we did not see in our earlier chart. This is not one of the solvents from our chart, but we can still recognize that it's polar aprotic because it contains no OH or NH bonds. This solvent is quite similar to DMF. This solvent is similar to DMF, but DMF would have a hydrogen in this position rather than a methyl group. But even though we haven't seen this specific solvent before, we can recognize that it is a polar aprotic solvent. And of course, we're familiar with the idea that water is a common polar protic solvent. It's easy to answer the question because we've memorized that polar protic solvents are better for SN2. Here's our answer. Solvent B is best for SN2. Now for credit, we need to justify our answer. So the answer is based on the idea that this is polar aprotic, and we should say why that's better. Polar aprotic is better because it solvates the nucleophile more loosely. Polar protic is worse for SN2 because it solvates the nucleophile more tightly. To finish up this video, I want to go back to SN2 reactions. So we've seen that polar protic solvents are worse for SN2 because they create more steric hindrance around the nucleophile. How do they create that steric hindrance? It's because a polar protic solvent creates a tight solvation shell around the nucleophile, whereas a polar aprotic solvent solvates the nucleophile more loosely. But what we haven't done yet is we haven't explained why the polar protic solvent creates that tight solvation shell, and we have to explain why the polar aprotic solvent solvates the nucleophile more loosely. So that's what I'm going to discuss in the remainder of this video. Now, I should mention that what I'm going to be talking about next is rarely tested. Most professors rarely write questions that require you to explain why the polar protic solvent creates the tight shell and the polar aprotic solvent solvates more loosely. So for most courses, what we're going to go over next is not going to be necessary for scoring points on exams. So as a result, you might not be interested in watching the rest of this video. But if you are interested in learning a deeper explanation for these trends, we'll cover that next in this video. So to repeat, the remainder of this video will deal with material that you might find interesting that will help you to understand these trends better, but which is rarely required for scoring points on exams. Next, we have to discuss what is a hydrogen bond. Remember, each time I ask a question, I hope you'll pause and give an answer. So I hope you've answered, what do you think a hydrogen bond is? Here's the answer. We can define a hydrogen bond as an attraction between a hydrogen with a large delta positive and an atom with a negative formal charge, or a delta negative. This might not be the official definition for hydrogen bond that you'll see in your textbook, but I think this is the best, clearest definition of what a hydrogen bond is. Now, this definition of a hydrogen bond will make more sense once you've seen some examples of hydrogen bonding, and we will be illustrating some examples soon in this video. Before we look at those examples, though, now we can discuss why it matters whether a solvent is protic or aprotic. Well, the reason it matters is a protic solvent contains a hydrogen with a large delta positive. An aprotic solvent does not contain any hydrogens with a large delta positive. For example, water is a protic solvent, and it does contain a hydrogen with a large delta positive. The hydrogen has a delta positive because it's less electronegative than oxygen. Remember, the electronegativity of hydrogen is similar to carbon. This is a large delta positive because oxygen is substantially more electronegative than hydrogen. There's a big electronegativity difference between oxygen and hydrogen, and that creates a large delta positive on this hydrogen. And for the same reason, because there's a big electronegativity difference between this oxygen and this hydrogen, there would be a large delta positive on this hydrogen. Remember that these molecules do have a lot of hydrogens, but none of them have large delta positives, right? For example, this hydrogen is bonded to a carbon. Well, remember that the electronegativity of hydrogen is similar to the electronegativity of carbon. So there's no reason for there to be a large delta charge on either this hydrogen or this carbon. All the hidden hydrogens here are also bonded to carbons, so there's no reason for there to be a large delta positive on any of the hidden hydrogens, because those hydrogens all are similar in electronegativity to the carbons that they're bound to. So OH and NH covalent bonds are important because they create large delta positive charges on the hydrogens. By the way, now we can understand why these are called protic and why these are called aprotic. Protic refers to a proton. Now, what is the symbol for a proton? I hope you know that the standard symbol for a proton is H+. The most important factor in organic chemistry is the formal charges. So the key thing about a proton is that it's a hydrogen with a positive formal charge. Well, there are no actual protons in water because this hydrogen doesn't have a positive formal charge, but it's getting close. It's close to being like a proton because it has a large delta positive charge. So when we call this a protic solvent, we don't mean that it literally contains a proton, so to speak. This hydrogen would not be considered a proton here because it doesn't have a positive formal charge, but it's close to being considered a proton because it has a large delta positive charge. Again, this hydrogen has a large delta positive charge, so the point is that these hydrogens behave similarly to a proton. A proton behaves the way that it does because it has a positive formal charge. And this hydrogen behaves similarly to a proton because it has a large delta positive charge. So the positive charge here is not as large as on a proton, but it's getting close to that. So that's where these terms come from. These are called protic solvents because they contain hydrogens that behave similarly to protons because they have a positive charge that's almost as big as the positive charge in a proton. And these are called aprotic solvents because the hydrogens in these solvents do not behave similarly to a proton. This hydrogen is not going to behave similarly to a proton because this is a near neutral hydrogen. This is a near neutral hydrogen with very little delta charge. So it's not going to behave very similarly to a proton with a positive formal charge. So that's where the term protic and aprotic solvent comes from. Next question, which types of solvents can engage in hydrogen bonding? Remember, this is the definition that we learned earlier for hydrogen bonding. So pause the video and determine which of these types of solvents can engage in hydrogen bonding. Here's our answer. Well, remember that a hydrogen bond involves a hydrogen with a large delta positive. Protic solvents have a hydrogen with a large delta positive. So polar protic solvents can engage in hydrogen bonding. An aprotic solvent does not contain any hydrogens with a large delta positive, and therefore an aprotic solvent cannot engage in hydrogen bonding. At least an aprotic solvent could not engage in hydrogen bonding with itself because it doesn't have any hydrogens with a large delta positive. Well, now we're ready to finish our chain of logic. Polar protic solvents can engage in hydrogen bonding, and the hydrogen bonding is what allows the polar protic solvents to form tight solvation shells around nucleophiles, which creates the steric hindrance that slows down SN2. Polar aprotic solvents can't engage in hydrogen bonding, therefore they solvate the nucleophiles more loosely and provide less steric hindrance to block the nucleophile. Here's a picture of what that tight solvation shell looks like. A solvation shell created by water molecules around a negative nucleophile. Do you see the hydrogen bonds here? So remember that because water, these are H2O molecules, water molecules, because water has OH bonds, the hydrogens in water have a large delta positive. There's a large delta positive on these hydrogens because of the electronegativity difference between the oxygen and the hydrogen. Hydrogens have large delta positives, and the delta positives on these hydrogens will be attracted by the negative formal charge on the nucleophile. Well, that's what a hydrogen bond is. A hydrogen bond is an attraction between a hydrogen with a large delta positive and an atom with a negative formal charge. So this hydrogen will be attracted to the negative charge, this hydrogen will be attracted to the negative charge. All these delta positive hydrogens will be attracted to that negative charge. We can show those hydrogen bonds with dots. These dots indicate the attractions between the nucleophile and the hydrogens. So the dots indicate the attractions between the delta positive hydrogens and the negative nucleophile. Remember, unlike charges attract. The partial positive charges will be attracted to this negative charge. Now, let's try to be clear about exactly which bonds in this picture represent hydrogen bonds. The hydrogen bonds are the bonds shown by the dots. This is a hydrogen bond, this is a hydrogen bond, hydrogen bond, hydrogen bond, hydrogen bond, hydrogen bond. Those are the attractions between hydrogens with a large delta positive and the nucleophile with a negative formal charge. So is this a hydrogen bond? No, this is not referred to as a hydrogen bond. This is referred to as an ordinary covalent bond. Now I know that could be confusing because this is a bond and it does involve hydrogen. But even though this is a bond that involves hydrogen, it's not referred to with the technical term of a hydrogen bond. Instead, it's just referred to as an ordinary covalent bond. Is this a hydrogen bond? No, it's just an ordinary covalent bond. What's this? It's not a hydrogen bond, it's an ordinary covalent bond. Is this a hydrogen bond? No, it's an ordinary covalent bond. This is a hydrogen bond. So notice that hydrogen bonds are shown with dots, and ordinary covalent bonds are shown with solid lines. To repeat, ordinary covalent bonds are shown with solid lines, and hydrogen bonds are shown with dots. The term hydrogen bond is a technical term. So even if a bond involves a hydrogen, we might, like this one, we might not refer to it as a hydrogen bond. This is not called a hydrogen bond, even though it's a bond that involves a hydrogen. This is just referred to as an ordinary covalent bond. The bonds shown with the dots here are the ones that we would refer to as hydrogen bonds. So my point is, don't confuse hydrogen bonds, shown with dots, with ordinary covalent bonds, which are usually shown with solid lines. The term hydrogen bond is a technical term that refers to an attraction between a hydrogen with a large delta positive and an atom with a negative formal charge or a delta negative. The term hydrogen bond appears a lot in chemistry and biochemistry, so it's important to have a clear idea of what a hydrogen bond is. So you can see that the hydrogens are forming a tight shell around the nucleophile, and this shell of solvent molecules around the nucleophile would decrease the rate of an SN2 reaction by creating steric hindrance that would block the nucleophile and make it difficult for the nucleophile to get access to the alpha carbon. This wouldn't occur with an aprotic solvent because an aprotic solvent cannot engage in hydrogen bonding. So here's an example with a nucleophile solvated by acetone, a polar aprotic solvent. This is an aprotic solvent with no OH or NH bonds. This aprotic solvent cannot create hydrogen bonds with the nucleophile, and therefore it's solvating the nucleophile more loosely. How is the solvent going to be attracted to the nucleophile? Can you figure it out? You might want to pause the video and ask what the attraction is between the solvent and the nucleophile. Well, I hope that you figured out that these carbons have delta positive charges, the carbons that are attached to the oxygen. Oxygen is to the right of carbon in the periodic table, so oxygen wants electrons more than carbon. So the oxygen will pull the electrons closer to itself, leaving a delta positive on these carbons. These carbons have delta positive charges, and those delta positive charges will be attracted to the negative nucleophile. But remember, so I'm showing the attractions with these dots, those attractions are not hydrogen bonds. Obviously, they're not hydrogen bonds because they're not an attraction between a hydrogen with a large delta positive and an atom with a negative formal charge. So here we have attractions, but they're not hydrogen bond attractions. By the way, technically these attractions would be called, ion dipole interactions. Technically the term for this is an ion dipole interaction because here's an ion and there's a molecular dipole in the solvent molecules. those attractions are not as strong as hydrogen bond attractions, and therefore the solvent does not form a tight shell around the nucleophile here. This nucleophile is solvated more loosely, which makes SN2 easier. Let's go through the logic of those delta charges one more time for this molecule. Oxygen is to the right of carbon in the periodic table. That means that oxygen is more electronegative than carbon. That means that oxygen wants electrons more than carbon does. Therefore, the oxygen will pull the electrons in these covalent bonds closer to the oxygen and further from the carbon. But electrons have negative charges. So if the oxygen is pulling the electrons in the covalent bonds closer to itself, that will give the oxygen an extra partial negative charge and leave the carbon with a partial positive charge, because the carbon has lost some of its electron density. Let's also, again, go through the logic for the delta charges for this molecule. So we know that the electronegativity of hydrogen is similar to the electronegativity of carbon. Well, we already discussed that oxygen is more electronegative than carbon, so this rule tells us that oxygen is also more electronegative than hydrogen. That means that the oxygen wants electrons more than hydrogen, so the oxygen will pull the electrons in this covalent bond closer to itself and further from the hydrogen. And that will again give the oxygen a partial negative charge and the hydrogen a partial positive charge. So far we've seen that the hydrogen bonding allows a strong, tight, close interaction between the hydrogens and the nucleophile, whereas the interactions over here, the dipole ion interactions, are looser and weaker. But why are these interactions looser and weaker, and why are these stronger and tighter interactions? After all, this interaction is an interaction between a delta positive and a negative, and this is also an interaction between a delta positive and a negative. So why are hydrogen bonds a stronger type of intermolecular attraction than what we see over here? Well, let's try to explain that. Well, it's based on the special qualities of a hydrogen atom. So what's special about a hydrogen atom? Well, do you know how many protons a neutral hydrogen has? You should know a neutral hydrogen consists of one proton. And how many electrons does a neutral hydrogen have? A neutral hydrogen has one electron. So what's special about a hydrogen is that it consists of just one proton and one electron. So if you pull the electron away, all that's left is just one proton. That's what makes a hydrogen special. If you pull this electron away from the hydrogen, there's no remaining electron cloud left. All that's left is the almost bare proton, so to speak. Compare that to another atom, such as a carbon. Well, a neutral carbon consists of 6 protons. And if it's neutral, it has 6 electrons. There's a whole cloud of 6 electrons around it. In the periodic table, we can see that what's special about hydrogen is that hydrogen is the first element in the periodic table. So it's the simplest element. A neutral hydrogen has only one proton and only one electron. You can see that from its atomic number of 1. All the other elements have more than just one electron when they're neutral. For example, here's carbon in the periodic table. From its atomic number of 6, you can see that a neutral carbon would have 6 protons, and therefore a neutral carbon would have a cloud of 6 electrons. So what's special about hydrogen is that a neutral hydrogen has only one electron. So if you pull that electron away, there's no electron cloud left, there's just a proton left. That's not true for any of the other more complicated elements in the periodic table. That's what makes hydrogen bonds special and stronger and tighter bonds. So if you look at this covalent bond, say, between the hydrogen and the oxygen, we know that a covalent bond consists of 2 shared electrons. One electron that was contributed to the bond by the hydrogen and one electron that was contributed to the bond by the oxygen. But we know that the oxygen is more electronegative than the hydrogen, so the oxygen is going to pull the electrons in the covalent bond closer to itself and further from the hydrogen. So a more accurate picture of this covalent bond is like this. Now I've drawn it to show that the pair of electrons in the covalent bond have been pulled close to the oxygen and far from the hydrogen. They're still being shared between the hydrogen and the oxygen, but they're being very unequally shared. The oxygen gets much more possession of this pair of electrons, and the hydrogen gets much less possession. That's the reason why we say the hydrogen has a delta positive charge. The hydrogen is partially positive because its electron has been partially pulled away from it. And what's left? What's left in this hydrogen when its electron is partially pulled away from it? Nothing but a proton. When this electron is pulled away from the hydrogen, there's nothing left in this hydrogen except this one proton. There's no remaining cloud of other electrons around this hydrogen. There's no remaining cloud of other electrons around this hydrogen, just that one almost bare proton. Well, it's very easy for that one small, almost bare proton with no electrons around it to snuggle up quite close to this negative charge. Obviously, that positive proton is going to be attracted by this negative nucleophile. There's no other electrons around to get in the way, so that proton can snuggle up in a tight, strong, close attraction with this negative nucleophile. That's the reason why this hydrogen bonding interaction is such a strong, tight interaction, because there's no cloud of electrons left around the hydrogen to interfere with the hydrogen bonding interaction. This hydrogen acts a lot as if it was a bare proton. It's not quite the same as a bare proton because it is still partially sharing these electrons, but it's somewhat similar to a proton. As we explained earlier, that's the whole reason why the water is called a protic solvent. The water is called a protic solvent because the hydrogens in the water act a lot as if they were bare protons. This is called a protic solvent because these hydrogens act a lot like bare protons because they've largely lost their electron, which leaves just a bare proton behind. That's the reason these are called protic solvents, because the hydrogens act a lot like a proton. Notice that that's quite different from these hydrogens attached to a carbon. This is not a protic solvent because remember that carbon and hydrogen have quite similar electronegativity, which means that the electrons in this covalent bond will be approximately equally shared. The electrons will be approximately equally shared between the carbon and the hydrogen. I tried to show that by drawing the electrons as being approximately halfway between the carbon and the hydrogen. So this proton is still quite close to its electron. This proton is quite close to its electron, and therefore the hydrogen doesn't really act like a bare proton. It doesn't have a large delta positive. Charge. That's why this is referred to as an aprotic solvent. It has hydrogens, but the hydrogens don't act like bare protons because they're still quite close to their electron in the covalent bond. Now let's examine this interaction again and see why it's not as strong and tight an interaction as the hydrogen bonding interaction. Well, this carbon has a delta positive because the electrons in these covalent bonds are being pulled closer to the oxygen than to the carbon. So the electrons are not being equally shared between the oxygen and the carbon. Since the oxygen is more electronegative than carbon, the oxygen will pull the electrons closer to itself. So here I've shown the two pairs of electrons being pulled closer to the oxygen than to the carbon. That's the reason why this carbon ends up with a delta positive charge. The carbon contributed 2 electrons to these two covalent bonds, but both of those electrons, and the oxygen contributed 2 electrons to the covalent bonds, but all of those electrons are being pulled closer to the oxygen than to the carbon. So in a sense, this carbon has almost lost 2 of its original electrons. The carbon hasn't completely lost them, it's partially sharing them, but only partially. It has unequal sharing of these electrons. So the carbon has partially lost 2 of its 6 electrons. That's what gives it its delta positive charge. But notice that unlike the hydrogen, there's still lots of electrons left around the carbon. Even after this carbon has partially lost 2 of its original electrons, the carbon is still surrounded by a cloud of other electrons. The carbon is still surrounded by 4 of its remaining electrons. And also, the carbon is still fairly close to this large cloud of electrons in this methyl group, and another large cloud of electrons in this methyl group. To repeat that, the carbon has partially lost 2 of its original electrons, but it's still surrounded by a lot of other electrons, still surrounded by 4 of its original electrons, and also the carbon is very close to the large cloud of electrons in this methyl group and another large cloud of electrons in this methyl group. Well, so all of those remaining electrons are going to help to repel this negative nucleophile and keep this interaction from being a close, tight interaction. The delta positive charge on the carbon will be attracted by this negative nucleophile, but it's not going to be a close, tight interaction because the nucleophile is also going to be repelled by all the remaining electrons that are still surrounding the carbon, both on the carbon, so to speak, and also in these 2 nearby methyl groups. The attraction between this delta positive and this negative charge is a fairly loose and distant attraction because it's being interfered with, so to speak, by the remaining cloud of electrons on the carbon and on these 2 methyl groups. Whereas in contrast, the attraction between the delta positive on this hydrogen and this negative charge, this is a close and tight attraction because there is no remaining cloud of electrons around this hydrogen to interfere with the interaction. All right, I hope that gives you a sense for why a hydrogen bond is a stronger, tighter, closer attraction than an ordinary intermolecular attraction between a delta positive and a negative charge. It's because when a hydrogen has a delta positive, there's no cloud of electrons left around the hydrogen to interfere with the hydrogen bonding attraction. But when any other atom has a delta positive charge, it's still going to be surrounded by a cloud of other electrons that can interfere with and weaken the attraction between the delta positive and a negative charge. Hydrogen is unique because a neutral hydrogen starts with only 1 electron, unlike all other elements. So when you pull that 1 electron partially away, there's no remaining cloud of electrons left to interfere with the interaction between the delta positive and the negative. Okay, I've taken my time trying to explain this, not because it's so crucial for getting problems about solvents correct, but because hydrogen bonding is an important phenomenon in chemistry and especially in biochemistry. Hydrogen bonding comes up a lot in chemistry and especially in biochemistry, and so you'll be much better off if you have a clearer understanding of what hydrogen bonding is and why a hydrogen bonding attraction is a stronger and tighter attraction than other types of intermolecular attractions between delta positives and negatives. And we've also gotten a deeper understanding of these terms protic and aprotic solvent. This is called a protic solvent because the hydrogen acts very similarly to a bare proton. And this is called an aprotic solvent because the hydrogens in this solvent do not at all act like bare protons. Act more like neutral hydrogens. By the way, let me make clear that when I say that a hydrogen bond is a strong, tight bond, I mean that it's stronger and tighter than an ordinary intermolecular attraction between a delta positive and a negative. A hydrogen bond is still a looser and weaker interaction than a covalent bond. So to repeat, a covalent bond is a stronger and tighter interaction than a hydrogen bond. I haven't necessarily drawn it that way. I haven't drawn these very tightly bonded to each other just so I have enough space. I suppose if I was going to draw this more realistically, I guess I should draw it more, I don't know, like this to show that this is a strong and tight interaction. So this is not a perfect picture, but anyway, my point is that covalent bonds are stronger than hydrogen bonds. Remember that covalent bonds are shown by solid lines, whereas a hydrogen bond or an ion-dipole interaction is shown by dots. These dotted interactions are intermolecular attractions between 2 separate molecules or ions, whereas the covalent bond is a bond within a single molecule. So again, this covalent bond is stronger than this intermolecular hydrogen bond, but this intermolecular hydrogen bond is stronger than this intermolecular ion-dipole interaction. So here's a summary of some of the ideas we've been talking about. Make sure that you've memorized this definition of what a hydrogen bond is. This might not be the same definition you see in your textbook, but I think this is maybe the best definition for a beginner to understand what a hydrogen bond is. We've seen that a protic solvent contains one or more OH or NH bonds, and as a result, a protic solvent contains a hydrogen with a large delta positive. As a result, a polar protic solvent can engage in hydrogen bonding. As a result, polar protic solvents form tight solvation shells around a nucleophile, as is shown in this picture, and therefore the polar protic solvent decreases the rate of SN2 by creating steric hindrance with this solvation shell that blocks the nucleophile from joining the alpha carbon. Remember, the big obstacle to SN2 is steric hindrance that blocks the nucleophile. Well, the logic is completely reversed in this column. An aprotic solvent doesn't contain any OH or NH bonds, so there are no hydrogens with a large delta positive, so an aprotic solvent cannot engage in hydrogen bonding, and as a result, the polar aprotic solvent has to solvate the nucleophile more loosely, as we've shown in this picture, and that more loose solvation provides less steric hindrance, which allows a higher rate for an SN2 mechanism. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.